Okay, wait, now something. Okay, it just takes a long, long time to do anything. Okay, are you recording? It's flashing, so I'm going to assume that you're recording. Okay, but how do we close this window? Okay, I assume that it's now working. So let's just go ahead and pretend that this thing is recording and see how it goes. Okay, sorry for the delay. It seems like my computer has a different problem every single class. Okay. At the end of the semester, I'm just going to throw it out the window. So don't walk. There's that little alley between just south of Rutherford building. The last day of class, don't walk in that alley, okay, because there'll be a computer flying out the window. Okay, today I would like to continue and conclude our discussion of the rotation symmetry and the role of rotation symmetry in quantum mechanics. So the algebra of rotation generators is the algebra that follows from the algebra of rotations of three-dimensional space. And that algebra, as you all are more or less familiar with, is generated by three rotations, J1, J2, and J3, which are the Hermitian operators that generate the rotations about the x, y, and z axes, respectively. And the question that we started to ask last time is, what possible Hilbert spaces are there which can be acted on by three Hermitian generators obeying this algebra? Okay. And that will describe for us the possible quantum mechanical systems with rotation symmetry. And what we found is that the n-dimensional representation of this group, or this algebra of symmetries, is a Hilbert space called Hn, describing a particle, or describing an object with spin equal to n minus 1 over 2. And that Hilbert space, which I denoted H sub n, where n, so H sub 1 is the Hilbert space of a spin 0 particle, H sub 2 is the Hilbert space of a spin 1/2 particle, H3 is the Hilbert space of a spin 1 particle, and so on and so forth. So let's just write H spin n minus 1 over 2. Is the Hilbert space which is spanned by a set of generators, typically denoted J comma M, where J here is the highest eigenvalue under J3, and M here is the labeling the J3 eigenvalue, and M in this Hilbert space runs between minus J and J, so it's some integer. And I actually suppose I should remind you that I introduced some normalization so that J was an integer, so that there's some factor of H bar in our definition of what we mean by the J3 eigenvalue of some state. And we also introduced these ladder operators, J plus and J minus, which were J1 plus or minus I, J2. And these played the same role as the raising and lowering operators in the algebraic description of the harmonic oscillator. The state, in particular, if you act on a state with a given J3 eigenvalue by J plus, it will increase the J3 eigenvalue. And you act with J minus, it will decrease the J3 eigenvalue. So, for example, the state with highest J3 angular momentum is annihilated by J plus. And in order to lower the eigenvalue of J3 angular momentum, we act with the J minus operator. And there's some sort of normalization constant here that we worked out last time. Or rather, we worked it out in one specific case, and I told it to you I just told you the answer because it's sort of easy to work out in the other cases. Okay. Okay. So I then stated for you, without proof, a sort of remarkable mathematical fact, which is that it turns out that every representation of the rotation algebra, SU2 or SO3, they're really different names for the same algebra as we discussed last time, is a direct sum of these H sub n's. Where I remind you that when you take the direct sum of two Hilbert spaces, you're just doing exactly what you imagine that you're doing. So, for example, H1 is the Hilbert space of a spin 0 particle, so it's just some one-dimensional Hilbert space spanned by a single basis element 0, 0, and H2 is the Hilbert space that's spanned by states of the form 1/2, 1/2, that's the spin-up state, but spin 1/2, and 1/2 minus 1/2. So that, for example, the direct sum of these two guys is the Hilbert space spanned by all three of those basis elements. If you want to think a little bit more geometrically, you could think of the Hilbert space H1 as the z-axis and H2 as the xy plane. That's a two-dimensional vector space. And then the direct sum, H1 plus H2, would be the three-dimensional space given by x, y, and z coordinates. And it turns out that this is a very useful way of organizing our thinking about the Hilbert spaces of spin systems in quantum mechanics. Okay. And so let me just remind you of a fact that I introduced last time, which is that if you take the Hilbert space of a spin S1 particle, and you tensor it with the Hilbert space of a spin S2 particle. So this would be what you would do, for example, if you had a spin S1 particle and a spin S2 particle that were sitting next to each other, and you wanted to write down the description of the entire Hilbert space that described both systems. Then that is the sum of the Hilbert space of spin S1 minus S2 plus the Hilbert space with spin S1 minus S2 plus 1, and so on and so forth, all the way up to the Hilbert space with spin S1 plus S2. Or if you want to use the notation that I introduced earlier, where you label the Hilbert spaces by the dimension of the representation, we would be saying something like H of the Hilbert space 2S1 plus 1, H2S2 plus 1 is the Hilbert space 2S1 minus S2 plus 1 plus so on and so forth. So what does this mean physically? Okay, this is actually a rather easy thing to think about physically, although when I write it down in that form, it appears rather complicated. So in order to understand this a little bit more physically, let's just consider the following very simple example. Maybe before I do so, I should pause and see if there are any questions. So let's consider the following simple example, which is the case where we have two spin 1/2 systems sitting right next to each other. So to take an interesting physical example, you could imagine that you have two electrons sitting right next to each other. Electrons have spin 1/2. And so the Hilbert space describing this, these two electrons sitting right next to each other, would be the tensor product of these two two-dimensional spin 1/2 Hilbert spaces. And what is that? That is the Hilbert space, which is spanned by the basis elements. Well, I would like to, just to keep my notation rather, let me write it out in its full gory notational detail once and for all, and then introduce a slightly simpler notation to keep track of it. So it's spanned by 4 states. So one state where the first electron is spin up, and the second electron is spin up. The second state where the first electron is spin down, and the second electron is spin up. A third state where the first electron is spin up, and the second is spin down. And a fourth where both of the electrons are spin down. Okay. And here I'm using the notation that we introduced when we talked about tensor products and entanglement, where I have a subscript that on these ket vectors that tell us which electron I'm talking about, and I'm using that cross inside a symbol, a circle symbol, to denote a tensor product. But we usually, in cases like this, we'll just use a slightly more compact notation. So I'll just call the two states, I'll just call that first state up, up. I'll call that second state down, up. The third state down, down. And the third state up, down, and the fourth state down, down. Okay. So this is a fairly conventional notation when discussing spin 1/2 particles. Sometimes you'll also see people denote these by pluses and minuses instead of ups and downs. In fact, I think that might be the notation in the textbook. Is that right? It's pluses and minuses? Okay, why don't I go ahead and use that notation instead, because it's completely equivalent. Okay. You can use whatever notation you like. In fact, I think on the problem set, maybe did I use plus minus? Okay, I'll go ahead and use that notation. Okay, good. Okay, and so the claim that I made is that I could view this Hilbert space as the direct sum of a spin 0 and spin 0 and spin 1 Hilbert space. Okay. I.e., the spin 1/2 representation tensored with another spin 1/2 representation is equal to the spin 0 representation and a spin 1 representation. If you think about it physically, this makes a good deal of sense. If you have two spin 1/2 electrons, two electrons with angular momentum 1/2, and they're both pointing in the same direction, it'll have spin 1. Okay. But if they're pointing in the opposite direction, it'll have spin 0. Okay. So that's a little bit of a physical basis for that statement. But let's work it all out in a little bit more detail. So the basis of that I wrote down above for this tensor product, so this tensor product basis is acted on by the usual angular momentum operators acting on the first and second electron, the first and second Hilbert spaces. And a full rotation acts on both simultaneously. So, for example, if you want to write down, let me try and use consistent placement of indices. If you want to write down the total angular momentum operator acting on the tensor product system, then that should be given by a rotation acting on the first guy tensored with the identity operator on the second, plus the identity operator acting on the first times the rotation acting on the second. Okay. What does that formula mean? That formula means something totally simple. It means that if you want to act with a rotation on the combined system, then an infinitesimal rotation on the combined system is a rotation on each one of the individual systems added together. Okay. Or another way of saying that, if you're, for example, calculating the J3 eigenvalue of some state, then if the first state has spin 1/2 and the second state has spin 1/2, then the total J3 eigenvalue is 1/2 plus 1/2 equals 1. Okay. So I've written it in this tensor product language just because that's the language that we usually use to write these things down formally, but hopefully that is something that should make pretty good sense to you. So, for example, if you calculate the total J3 angular momentum of the state plus plus, then that's equal to 1 times plus plus. Okay, I suppose I should use, I had an h bar there in my definition, so I'll just divide out by an h bar here. Whereas 1 over h bar times J3 total of the state plus minus is equal to 0. Okay. That has no units of angular momentum in the z direction. 1 over h bar J3 total of minus plus likewise has no units of angular momentum. And 1 over h bar J3 total of the state minus minus has -1 units of angular momentum in the z direction. Okay, is everything clear so far? Okay. Any questions? So the claim that I made earlier is that I can organize these 4 states into a basis in which it looks like it's a spin 0 system combined with this, along with a spin 1 system. Okay, so what do we mean by that explicitly? Well, clearly, if I want to write this as a spin 1 and a spin 0 system, the spin 1, the direct sum of the spin 1 and spin 0 system is the span of the 4 elements 0, 0, which is the state with no spin, along with the 3 states in the spin 1 system. And if you just look at these formulas up here, you can begin to see exactly how that's going to have to work. Okay. So let's look at this state here. Okay, that's the state with 1 unit of angular momentum in the J3 direction. So that has to be this guy plus plus. And likewise, this guy down here has to be the 1 minus 1 state. And these 2 states here, the plus minus and minus plus states, must be some linear combination of the states 0, 0 and 1, 0. Okay. And so the question we then have to answer is which linear combination is which. So how do we go about answering that? Well, that's very easy. If you want to identify the state 1, 0, well, 1, 0 is just found by acting along with some normalization factor that we actually worked out last class, with the lowering operator J minus, okay, on the state 1, 1. Okay? Right? So a state with no units of angular momentum in the spin 1 representation is found by acting with the lowering operator on the state with 1 unit of angular momentum in the spin 1 representation. And what is that? Well, that's 1 over root 2 times the lowering operator acting on the plus plus state, which is the sum of plus minus and minus plus. Okay. Because the way that when you act angular momentum just adds between the two systems. So J minus acting on a state plus plus is the sum of two things, the J minus acting on the first spin and doing nothing on the second spin, plus J minus acting on the second spin and doing nothing on the first spin. Okay. And so that means that the state 0, 0 has to be the state in the Hilbert space that is perpendicular or orthogonal to all of the spin 1 states. So it has to be that other linear combination plus minus 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 plus. Okay. And in fact, for historical reasons, the spin 0 state built out of two spin 1 half particles is known as the EPR state because Einstein, Podolsky, and Rosen, when first trying to discuss mysterious properties of entanglement in quantum mechanics, were the first people to really write down the state in this form. At least I think so. I'm not entirely sure. But at least they were the most famous people to do so. And so the state is named after them. Okay. I should also mention that the state is... yes, question.
Sorry, what was the argument to say that it was just you change sign?
The point is that I want to have something which has... So if you look at this H1 and H3, I want the spin 0 states to be orthogonal, to have 0 inner product with the spin 1 states. So, and we know that the states plus minus and minus plus, there must be some linear combinations of those that give you the two different spin 0 states, the 0, 0 state and the 1, 0 state. And so you just need to find, so I've identified the 1, 0 state, so I need to find that linear combination which is perpendicular to it. And indeed, if you look at it, this definition was chosen precisely in order for this inner product to vanish. Or I could have minus that. Yeah. Oh, yes, absolutely. So what did I do? I just demanded that it was unit normalized and orthogonal. So I know that it's this up to an overall phase. Okay. Convention, so that overall phase is just some convention, right? It won't actually matter for the physical definition of the state. Good question. Yeah. I should mention that this is actually very important physically. It's this linear combination which is responsible for superconductivity in the BCS theory of superconductivity. Okay. So why is that true? In certain materials, so a metal is something which has a lot of electrons floating around, okay, and those electrons will interact in some way. And it's possible for those electrons to form bound states of various sorts, depending on what kind of interactions the electrons have, namely depending on what sort of metal we're considering. And it turns out that in certain kind of metals, at sufficiently low temperatures, it's possible for these electrons to pair up together. And as we've seen here, there are various different sorts of ways that they can pair up. And indeed, what we've seen here is that it's possible for them to pair up together into a spin 0 state. And what's interesting about spin 0 states? Well, states with integer spin are bosons. Okay. And as we learned in our study of quantum statistical mechanics, unlike fermions, bosons can form a Bose-Einstein condensate. Okay. And so what a superconductor is in the BCS theory of superconductivity is it's a particular metal at sufficiently low temperature where the electrons bind together into these spin 0 states and then form a Bose-Einstein condensate at very low temperature. Okay. And Why is that a conductor? Well, you have a very large number. So these bound states of electrons carry charge. Okay? And what we've learned is that when you have a lot of low-energy charge-carrying excitations, that means that it's very easy to move charge around the system, i.e. the system is a very good conductor. And so, indeed, it is this business about combinations of spin 1/2 particles forming spin 0 states, along with the study of systems with Bose-Einstein statistics that we saw earlier, that is really the feature that's responsible for superconductivity. So this plays a crucial role in the BCS theory of superconductivity. Okay, good. I should also make one sort of historical comment, okay, which is that there were various coefficients that we worked out in this particular example. Coefficients like 1 over root 2, minus 1 over root 2, and so on and so forth, which are the coefficients that arise when you try and write the tensor product Hilbert space of two spin systems, of two spins in terms of a bunch of direct sums. Okay. And these coefficients have a name. They're known as so-called Clebsch-Gordan coefficients. For doing things like atomic physics, nuclear physics, and so forth, they're actually very important. In the days before computers, people would write whole books full of Clebsch-Gordan coefficients. I've even heard the story about the guy who obtained the movie rights to the book. Sadly, yet the movie has not been made. But thankfully, in these days of Mathematica, we don't actually need to worry too much about computing them. As you can see here, there's a completely straightforward algorithm that you could probably work out for yourselves based on what I've done here for figuring out exactly how to construct these Clebsch-Gordan coefficients. You know, it's rather straightforward. You start with the highest spin state, you know what that is, and you start acting with lowering operators. Then you look at the next highest spin state, you start acting with lowering operators, and then you try and normalize everything and make sure everything is, all these different Hilbert spaces are orthogonal. That's some algorithm that would let you compute these coefficients. Okay. I won't say too much more about it, except that it's a completely straightforward algorithm that we could work out if we wanted to. Okay. Are there any questions so far? Okay, good. Okay. So let me now ask the following question. Okay. So I began our discussion of Hilbert spaces that were representations of the angular momentum algebra by discussing a particle in 3 dimensions. So a particle in 3 dimensions is described by an infinite dimensional Hilbert space and in particular, it's the Hilbert space of wave functions that describe the particle in 3 dimensions, which in position space, for example, you would write something like this. Okay. So it's the set of all such wave functions. And I've already told you that every Hilbert space that is a representation of the angular momentum algebra is a sum of all of the irreducible representations labeled by those integers n. So that means that this Hilbert space must be a direct sum of the h sub n's that I wrote down above. Can anyone guess for me what that sum is? Okay, it's got to be a sum of an infinite number of them. I'll give you a hint. You've seen it already. I know you have. You just didn't know that that's what, it's yet again in this class. You've seen the answer to this question. Okay, you know what the sum is, but you just gave a name to those objects that you were studying, which made it a little obscure that you are actually doing some very simple group theory of the rotation algebra. Anyone have a guess? And indeed, you worked out those Clebsch-Gordan coefficients. You just called them something slightly different. You called them spherical harmonics. So in fact, the theory of spherical harmonics is nothing more or nothing less than this fact about the representations of the rotation group applied to a particle moving in 3 dimensions. So let's understand exactly what that means. Okay. So how do these rotation generators act under under one of these angular momentum generators? So these wave functions are acted on by the rotation generators Ji in the way that we have already discussed. So Ji is minus I h bar times epsilon I jk xj d by dxk. Okay. Or, using our vector calculus notation, minus I h bar, the cross product of x with the gradient operator. So, one of the things that we have learned in this class over the last week or so is that these Hilbert spaces H sub n that describe a particle with a given spin, okay, that describe the spin S representation of the rotation algebra, are characterized by the fact that the Casimir J squared is a constant. So the thing that we want to do in this case is work out explicitly what this Casimir is when we act on a particle moving in 3 dimensions using this particular differential operator. Okay. So this is actually a calculation that you've done. You did it when you worked out, for example, Laplace's equation in spherical coordinates or the Schrödinger equation in spherical coordinates. So I won't waste your time by going through the answer. I'll just write it down for you. So you get a 1 over sine squared theta times d by d phi squared plus 1 over sine theta times d by d theta of sine theta d theta. Okay. So that's in the usual spherical coordinates. Okay? And what is the operator J3? Well, in spherical coordinates, that's minus I h bar d by d phi. Okay. So, if you want to construct a representation with spin J in this Hilbert space of wave functions in 3 dimensions, then what you're looking for is you're looking for a set of n functions, where n is 2j plus 1, which all have the same value of j squared, and which are organized into a basis where they're all eigenstates of J3, and they're related by the raising and lowering operators. And we have a name for that basis of functions. We call those the spherical harmonics. So, what we're looking for is a basis of functions on the 2-sphere, that is to say, of theta and phi, which make up the irreducible representation of dimension n, which we could say equal to 2L plus 1. Okay. I'm using L here instead of S or J because, as we noted earlier, when talking about orbital angular momentum, conventionally people use the symbol S, or L instead of S or J. Okay. And then we want, so we'll usually give so I'll give a name to those functions. I'll call them YLMs, okay, where M runs from minus L up to L. And that's just a particular notation that we use where YLM is some function of theta and phi, which is completely analogous to the state LM that I introduced when I studied the abstract theory of representations of the rotation group. Okay. So, for example, YLL is the function of theta and phi, which is defined by the property that it is annihilated by J plus. So J plus acting on YLL is equal to 0. And it's straightforward to work out what J plus and J minus are in this Hilbert space. So remember I told you, I wrote down up above that J1 and J2, J1 is y d by dz minus z d by dx. J2 is x d by dz minus z d by dx. J plus is some complex combination of those. So this is some first-order differential equation that is obeyed by YLL, which you can solve. And you've already seen the answer, so I won't bother working it out for you. The only point that I'll mention is that it has an e to the I L phi here. That's just the statement that the eigenvalue under J3, which was d by d phi, is equal to L, and it's got some function of theta that's found by solving that differential equation and demanding that everything is normalized properly. And then the YLMs are found by acting with J minus, which again is some linear differential operator on YLL. Okay. And so that's some horrible function that I guess we could call P sub LM of theta times e to the I m phi. Okay. And we could go ahead and work it all out in horrible explicit detail if we wanted to. In fact, these PLMs have some names. I think they're called the Chebyshev polynomials of cosine theta. Is that right? Okay. Is that right? Or are they the Legendre polynomials? Okay. I can never get these various different families of special polynomials straight in my head. The good thing is that you don't really need to, okay? Because, when you studied these previously in your lives, they were just introduced as some formal nonsense that you really had no idea what was going on. But now you really know exactly what the YLMs are. They're the spin L plus 2L plus, they're the spin L representation of the rotation group, just written as functions of theta and phi. Okay. They're those functions of theta and phi that live in the spin L representation of the rotation group. Okay. And the indices L and M are nothing more or nothing less than the indices J and M that I use when I described this Hilbert space formally when talking about the spin 0, spin 1, spin 2 particle, and so forth. Okay. So, for example, Y00 is just a constant. That's the spin 0 part of the Hilbert space of functions in three-dimensional space. The Y1, 1, 1, 0, and 1 minus 1 are the spin 1 representation, and so on and so forth. And then the full wave function psi of x is then expanded in a sum over all of these YLMs of some function of radius times YLM of theta and phi. Okay. So this is the statement that the YLMs form a complete basis of functions for functions in three-dimensional space. Okay. And so there's another name for this formula. Okay. This formula is also the statement that the Hilbert space of our three-dimensional particle is the sum of the spin 1 0 Hilbert space plus the spin 1 Hilbert space plus the spin 2 Hilbert space, and so on and so forth. Okay. So spin 0 plus spin 1, and so on and so forth. Okay. So indeed, I wasn't lying to you when I said that every representation of the rotation group is a finite sum of these guys. Question?
When you wrote the two sums here for the phi of x, is that just like an arbitrary wave function?
Oh, yeah. Oh, you mean what this guy is?
No, just the whole thing.
Oh, yeah. So an arbitrary, yeah. So exactly. So any normalizable psi of x. Okay. I didn't quite. I don't know what that word was supposed to. Any normalizable psi of x has this form. Okay. Yeah.
The coefficients, I guess, can get into the R function.
And yeah, exactly. So, of course, the psi LMs of R will depend on what problem you're studying. Okay. If you're studying the hydrogen atom, for example, which is probably where you work this out in the most detail, then you need to use the fact, for example, that let's say that your Hamiltonian is 1 over 2m times p squared plus v of r. Okay, that's a rotationally invariant system. So we'll want to organize our Hilbert space into simultaneous eigenstates of H and the rotation generators. And in order to do that, you need to work out what the Laplacian is in spherical coordinates. And what is it? Well, you know that it's so it's got some radial piece. Okay. Sorry, there's a square there. So minus h bar squared times d by dr squared. Okay, this is just stuff you work out. I mean, you've done it before. Okay, it's got a 2 over r d by dr. That 2 comes from the fact that we live in 3 dimensions. And then it'll have something that involves the theta and phi directions. And you know that because this operator, but you know that because p squared is rotationally invariant, it's got to be a second-order differential operator that commutes with J1, J2, and J3. Okay, and there's only one such differential operator. We've already worked it out. It's this quadratic Casimir J squared. So you know that everything involving the theta and phi directions has to be that guy J squared, because it's the second-order differential operator that commutes with all of the J's. Okay. And so then you could go ahead and use that to expand your wave function up here in terms of the spherical harmonics, in terms of these representations. Then when you work things out in that basis, you're working in a basis where you have simultaneous eigenstates of energy and angular momentum, and you're left with some one-dimensional wave equation for these psi of r's here. Okay, and J squared, of course, as usual, is L times L plus 1. Okay, so you're left with some wave function, some wave equation on these psi of r's, which is effectively some one-dimensional wave equation. And so, for example, in the hydrogen atom, one can go ahead and solve that explicitly. Okay. Actually, I'll tell you something curious, which is that although in the hydrogen atom you solve the radial wave equation using just by solving some stupid differential equation. Okay. In fact, it's possible to completely solve the hydrogen atom without solving any equations whatsoever. You can solve it completely based on symmetries. That's because the 1 over r squared force that attracts an electron to the center of the proton is just the same 1 over r squared force that appears in the Kepler problem. And the Kepler problem has some obvious symmetries. It's got a rotation symmetry. It's got a time translation symmetry. Corresponding to those two symmetries are the conserved quantities of energy and angular momentum. But it also has a secret symmetry that nobody ever told you about, unless somebody told you about it. Did somebody tell you about it? Okay. There's another secret symmetry of the Kepler problem of a particle moving in a 1 over r squared potential. I wish I remembered the name of the symmetry. What's it called again? It's the Runge-Lenz vector. Okay. So there's this thing called the Runge-Lenz vector, which is a secret symmetry of the Kepler problem and of the hydrogen atom. And actually, it means that for the hydrogen atom, you actually have not a 3-dimensional rotation symmetry, but I think it's a 4-dimensional rotation symmetry, okay, generated by angular momentum and this Runge-Lenz vector, okay. That allows you to completely solve for the spectrum of the hydrogen atom without ever solving a single differential equation, okay. And if there's one thing that you should learn from this class, it's that if you can avoid solving a differential equation, you should, okay. If there's a way of solving a problem completely in terms of symmetries, then not only is that usually easier, but it usually reveals something very important about the dynamics and the structure of the system you're studying. This SO4 symmetry of the hydrogen atom, following from the Runge-Lenz vector, is very hard to sort of wrap your head around geometrically. I've never seen a completely satisfactory treatment of the sort that I would actually do it in class. But if anyone, you should go to the Wikipedia page, okay, and look at it. It's pretty cool. Okay. It's very hard to imagine how the hydrogen atom can have a symmetry of a particle sitting in 4-dimensional rotationally in space instead of 3-dimensional space. There's some way of visualizing it in terms of some complexifications of the system, but I haven't really. I don't really remember exactly how it goes. Okay, it's pretty cool though. That was just a sort of bit of a side inspired by your question. Are there any other questions? Are there any questions on the theory of rotations, angular momentum, so on and so forth? This is all stuff that you've in principle seen before. So in a sense, this last week has been a bit of a review, but hopefully it's been a review from a slightly more systematic perspective than what you've seen before. Any questions? Yes.
What was the justification again for going to J squared?
Ah, good. Well, what is P squared? Okay. P squared is an operator, okay, and it's rotationally invariant. Okay. The length, so P is a vector, okay, it's a momentum vector, and the length of a vector is independent of rotations, is rotationally invariant. Okay. What does that mean? That means that P has to commute with all of the P squareds. The P squared has to commute with all of the J's. Okay. Right? That's what it means for something to be rotationally invariant. The statement that the length of a vector doesn't depend on rotations of that vector is the statement that if you write down P squared, for example, it has to commute with these rotation generators. And P is also a second-order differential operator, so it's got to involve two derivatives of those thetas and phis and so on and so forth. And we've discovered only one differential operator that's second-order in these derivatives that commutes with all of these guys. And so that's the thing that we call J squared. Okay. Now, I gave you a very slick argument for why that had to be true. Of course, you could just work it out. I mean, you have explicit expressions for J1, J2, and J3. You could work out J squared. It's J1 squared plus J2 squared plus J3 squared. And you could just go ahead and write out the Laplacian in spherical coordinates, and you would find that this equation is true. I assume that you've done that. So I'm not, everyone should see the Laplacian work written out in spherical coordinates once and only once in their life, because it's a sort of gnarly derivation. You should definitely work that out yourself if you're not convinced of it. It's a good question. Other questions? Okay. Let me now introduce something which is a slightly more sophisticated version of the rotation algebra. So in particular, what I would like to do is I would like to talk about the symmetries of Newtonian physics. And in some sense, what I'm going to present now is a bit of a warm-up in preparation for our study of relativistic quantum mechanics later on in the semester. So, we've seen that, for example, rotation symmetry is a useful way of organizing our thinking about certain systems in quantum mechanics. But in Newtonian physics, the equations of motion of Newtonian physics actually have a larger and more interesting set of symmetries known as the Galilean symmetries. What are they? Well, they are the translations. So if you have a vector and you translate it, then that's an element of the Galilean group of symmetries of Newtonian physics. That's just a statement that if you have a laboratory and you do an experiment, and then you take the laboratory and you move it over 1 foot to the left, and you do the same experiment, then you won't see any difference in your experimental outcomes. So that's a symmetry of Newtonian physics. There is a rotation symmetry, where vectors all get acted on by these rotation matrices R. There are time translation symmetries, where you take your time coordinate and you relabel it by shifting it by a constant. So these are all rather obvious, and indeed, these are symmetries not just of Newtonian physics, but in special relativity as well. And there's a final symmetry, which is slightly less obvious, and which is true only in Newtonian physics, rather than in special relativity. And that is the symmetry of a Galilean boost. Okay. So what do you do in a Galilean boost? Well, you take the x-coordinate and you add to it a vector v times the time coordinate. Okay. So what is that? Physically, that says that you take one frame of reference and then you go to another frame of reference that is moving with some constant velocity vector v with respect to your first frame of reference. And the equations of Newton's laws, will be invariant under that change. For example, Newton's equation F equals ma involves the second time derivative of the position of an object. So if you shift x by something linear in t, that'll get killed by the second derivative, and the equations of motion are invariant. Or to put it another way, if you take your laboratory where you're doing some experiment, you put it on a train moving at constant velocity, and you perform experiments in that laboratory, as long as you're not experiencing any acceleration due to the train, the outcome of those experiments will be independent of the velocity of the train. And as you know, in special relativity, of course, that is not true, and the Galilean boost symmetry is replaced by something slightly more sophisticated, the Lorentz boost. Okay, so these are the symmetries of Newtonian physics. And if you want to work out the algebra of symmetries, what you want to do is find the differential operators which generate these symmetries. Okay. So the translations are generated by some momentum operators, so minus I h bar d by dxi, as usual. The rotations will be generated by some angular momentum vectors, so I h bar epsilon I jk. Not be neurotic about placing my indices. Okay, but now my pen is not working. Okay, good. Epsilon I jk, xj, d by dxk. The generator of time translations is usually called the Hamiltonian, of course, and that's I h bar d by dt. And in order to understand what the generator of the Galilean boost looks like, let's just note that under a Galilean boost, if you think about an infinitesimal Galilean boost, and you write this, okay, now my pen really isn't working. Okay, there we go. If you write this as x plus delta x, then delta x is vt. Or, if you write that in terms of an infinite, if you think about delta x as some infinitesimal differential operator times x, then it's going to be, that conventional I h bar times t times d by dxi. So if you want to understand that a little bit more systematically, just remember that a translation x goes to x plus constant is given by e to the ip times a constant acting on some function of x. And so likewise, if you want to take x not to x plus a constant, but x plus a constant times time, then you need to act on that some function of x with the operator e to the constant times c, where c is that differential operator that I've written down here. That's t times d by dx. Okay. Is that clear? Should I say a few more words about that? Good. Okay. So this allows us to work out the algebra of commutators between these various generators of the Galilean group of symmetries. So there are going to be a lot of zeros in these commutation relations. So, for example, time translations and spatial translations commute with one another. Time translations and spatial rotations commute with one another. And one can actually check, it's very easy to see, just given this algebra here, that the commutator of p with c is equal to 0, just because d by dx commutes with d by dx. Okay? And there are really only two non-trivial commutators here. The first is the commutator of j with p. Okay. Why is that commutator non-zero? Well, j is a rotation and p is a vector. And what do vectors do for a living? Vectors rotate for a living. Okay. The definition of a vector is something that rotates. And what does it mean to rotate? It means that it gets acted on by the rotation generators. And indeed, this is just I h bar, if you work it out, epsilon I j k pk. So that's just the statement that if you take a vector p and you rotate it, then infinitesimally under the rotation, it picks up something linear in p. That's given by the right-hand side of this equation. And there's one final And likewise, these C's also form a vector, and so they have a very similar algebra, epsilon ijk times ck. And finally, H with Ci, what is that? Well, we can just work that out quite explicitly just by comparing the equation for H with the equation for C, because you've got a T appearing in C and a d by dt appearing in H. So that's just I H bar times, so the d by dt kills the T, and we get d by dx. So this is Pi. Okay, so this is the algebra of symmetries of Newtonian physics. Okay. And in particular, this is the algebra of differential operators that generate these symmetries. In a mechanical theory, I can't spell properly, in some sort of mechanical theory, say some classical mechanics theory, these will be represented by what are known as charges. That is to say, i.e., by functions on phase space that generate these symmetries via Poisson bracket. Remember that in the Hamiltonian formulation of classical mechanics, the infinitesimal variation of some observable under a symmetry is given by its Poisson bracket with some generator. Okay, I guess I called them generators, not charges. Okay. Okay, I'm going to call them charges. Okay. Because it's important, actually, it's going to be important in a minute that I distinguish between the generators as differential operators and the generators as functions on phase space. And likewise, in quantum mechanics, they will be represented by operators that act on some Hilbert spaces. Okay. Now I'm going to tell you another secret. I'm telling you a lot of secrets this class. It's just like a Dan Brown novel. Okay. This is a secret that you should have learned in your classical mechanics class, but you almost certainly didn't. Okay. Maybe you did. I don't know. If you did, don't ruin it for everyone else. Okay. The algebra of, so far, in all of our examples of symmetries, the algebra of charges, the algebra of functions on a phase space when you take their Poisson brackets, is equal to the algebra of the differential operators. But in particular, the algebra of charges, it turns out, is not always equal to the algebra of symmetries. By which I mean, it's not always equal to the algebra of differential operators. In particular, they can differ by what are known as central charges. So what is a central charge? A central charge is an additional term on the right-hand side of the commutation relations And this term can't be an operator, it just has to be a number. So this term which will commute with everything else. Okay. I should say a little bit about the name central charges. It's called a charge because it's something else that appears in the algebra of symmetries. When you think about it as a set of operators that act on a quantum mechanical system, or as a set of functions on phase space that have a particular algebra of Poisson brackets. And it's called central because in mathematics, the word center refers to something that commutes with everything. So that's a bit of mathematical terminology. And the reason why you almost never learn about this is that for most groups, and in particular for most algebras, like, for example, the rotation algebra, such terms cannot be added, or in particular they must be equal to 0, or else you have some violation of the Jacobi identity. But the Galilean group is the first example of a group that we have encountered for which such a term is allowed. And in particular, Pi with Cj was equal to 0 for the algebra of differential operators. That can become a term that looks like this. Pi with Cj can be equal to I times a constant times delta ij. So what that means is that a representation of the Galilean group is specified not just by a spin, but also by a number called M. And so the question that we would like to then ask is, what is the physical interpretation of this number M? Now, I guess I've given you a little hint by calling it M as opposed to something else, but let's go ahead and think about it. Okay. And in fact, this can even arise in classical mechanics, this feature where your algebra changes by the addition of this extra term. So let's just even consider classical mechanics. And let's consider a particle of mass little m. And let's forget about a potential, anything like that. Let's just consider a free particle whose Hamiltonian is 1 over 2m p squared. And the Lagrangian is 1/2 m x dot squared. So we would then like to ask, what is the conserved quantity associated with the Galilean boost, which will allow us to identify the generator C. And here, I'm just going to consider a particle of mass m in one dimension, so I don't have any vectors floating around. Okay, C is just has no index. It's C1, if you want to call it that. Okay. So let's use the Nother procedure. Okay. So let's remember, so what happens under a Galilean boost? Under a Galilean boost, x goes to x plus epsilon t. And epsilon could be taken to be very small for an infinitesimal Galilean boost. the Lagrangian, and so x dot goes to x dot plus epsilon, and so the Lagrangian 1/2 m x dot squared will go to 1/2 m x dot squared plus epsilon m x dot plus terms that are higher order in epsilon, so that the variation of the Lagrangian under a Galilean boost is the time derivative of epsilon m x. So I remind you that when you shift your Lagrangian by a total time derivative, the equations of motion are unchanged. We saw that earlier in this course. And so what this means is that under an infinitesimal Galilean boost, the equations of motion are unchanged, as we expected. Okay. And now we would like to understand what the conserved quantity is associated with that symmetry. And so we need to use the Nother procedure. Okay. So let me just remind you of how that works, although you've seen it presumably in your classical mechanics courses. So under a symmetry where x goes to x plus delta x, and the Lagrangian goes to the Lagrangian plus delta L, where delta L is some total derivative. Why don't I not use J, because I've used it earlier. Let's call it Q dot. The variation of L can just be found by thinking about L as a function of x and x dot. So it's dl by dx dot, dl by dx times delta x, plus dl by dx dot times delta x dot. And we can rewrite this as dl by dx minus the time derivative of dl by dx dot, all times delta x. Oops. Plus the time derivative of dl by dx dot times delta x. Okay, I haven't done anything there, really. Except now that you notice that this quantity here is the Euler-Lagrange equation, i.e. the equation of motion. So that's equal to 0 for a solution of the equation of motion. So that if your Lagrangian is unchanged under an infinitesimal deformation, that means that this quantity here, dl by dx dot times delta x, is a constant of motion. And more generally, if the Lagrangian is not unchanged, but changes by a total derivative, then that implies that d by dt of dl by dx dot times delta x minus q is a constant of motion. Are you guys familiar with this? You've seen this. So hopefully you've seen this in your classical mechanics courses. This is the derivation of Nother's theorem from the Lagrangian point of view. And for the Galilean boost, I don't know what that word is. Boost. Q was equal to mx, and delta x was equal to vt. So that means that the constant of motion is equal to dl by dx dot, otherwise known as, v was equal to epsilon, and I factored out an overall epsilon, so I should really just put a t there for an infinitesimal Galilean boost. So the constant of motion is going to be dl by dx dot, otherwise known as the momentum p, times t, minus q, which was mx. Okay. So what have we learned here? We've learned here that the function on phase space of the particle, which generates the Galilean boost symmetry, is pt minus mx. And what is the point? The point is that the Poisson bracket of this with p is not equal to 0. If you ignored that second term that came from the total time derivative, you would see that c is t times p, which indeed is actually the equation that's true of the differential operators. P was d by dx, c was t times d by dx. But you see that because of that total time derivative term, there's a correction, and you get minus m. Or, in terms of commutators, quantum commutators are equal to I h bar times classical Poisson brackets. You get I h bar times m. So, indeed, we see that for classical and quantum systems, there are indeed these new terms that appear in the symmetry algebra when you study systems with Galilean symmetry. And so a physical system with Galilean symmetry is not just specified by one number j, which is a half integer, but rather by two numbers, a half integer j, as well as some continuous parameter m, which formally appears as a new term in the algebra of symmetries, but physically is interpreted just as the mass of the object that you're considering. So, the fact that particles in Newtonian physics are characterized by their mass and spin, I guess I should say quantum physics. Is a consequence of Galilean symmetry. So, I think it's appropriate at this point to step back and think a little bit about what you've seen in your lives as physicists. The fact that objects have mass is something that you were taught so long ago that you probably stopped even asking why it was true. Now, you've learned, really, that, in fact, the fact that objects have mass is a deep consequence of the symmetries of nature. And in particular, we've seen that in Newtonian physics, and for those systems that can be described, at least approximately, by the laws of Newton, the origin of mass is seen as a consequence of some new feature of the symmetries of the theory. And indeed, the fact that the objects are characterized by two fundamental parameters, their mass and spin, is simply seen as a consequence of this set of symmetries. And indeed, this logic can be extended. For example, if you include other symmetries, such as the gauge symmetries associated with electromagnetism, then you will see that objects are characterized by mass, spin, and charge. Or if you generalize this, as we will later on in this course, to special relativity, you'll see that the parameterization of fundamental particles in terms of mass and spin is generalized to take into account the structure of special relativity, and one can encounter more generalizations different types of spin. Spin gets more complicated in special relativity. Mass gets more complicated in special relativity, of course. But I think this is a great time to really sit back and think about why it is we characterize physical systems using the data that we do, and to see really that it's all a consequence of the symmetries of those systems. Okay. So let me stop here, and I'll see you guys next Wednesday.